Okay, I guess we can start, I think. 1, 2, 3. Hello. Good morning, everyone. Thank you for choosing this session. My name is Dudczak. I will tell you a bit about my small educational project, during which I was teaching computers to play games. As you know, programmers are lazy, and this is the ultimate laziness. So I want computers to play in games for me, so I don't have to. And the subtitle here is the only ML machine learning presentation you will ever need. Why such a bold statement? You will see in a minute, while listening about my ups and downs, that teaching computers to play games is a really nice way to practice your ML skills. And during the working on a particular game, which we can treat as a problem, you might encounter problems which are quite common when you start dealing with the machine learning problems. I encourage you all also to read more after this presentation, so I will not cover everything. Nevertheless, I hope that you will find this interesting. So, we want to teach computer to play games, the games as you see in the background. But before that, a few words about me. I work at Allegro. Allegro is the biggest e-commerce site in Poland. I'm involved in Java-related projects since quite a while, and also doing Python a bit, especially in the area of data science. On my daily basis, I'm responsible for the Allegro search engine, and search engine in which we are using machine learning every day. I was also, and I am still, a bit involved in the Poznań Java user group, and also in this small, humble conference. So let's go. Where to start? We want to teach computer to play game, so we need to have a game. How to get such a game? In which programming language should we program this? In terms of data science, the answer is quite simple. As the Python is a lingua franca of data science, and most of the new frameworks are developed with Python bindings or in Python itself, this is no-brainer. We will do that in Python. So if we are doing the whole thing in Python, maybe we will also find a game written in Python to hack it, to plug our machine learning or artificial intelligence in that game. So while I was looking for the game which would be suitable to do that, I came across Pygame, which is a pretty robust and battle-tested, if you can say that, for the game library, which allows you to write simple arcade platform games easily. So it's not. It deals with all the scaffolding, all the boilerplate code for you, so you can write a nice game in 100-something lines of code. So, as a subject of my project, I decided to use a game called Shmoop, which was the part of a tutorial for kids, in which the children were taught how to program to write games. So. A bit of a source code, since this is a technical conference and source code looks awesome on this cinema screen, so I was tempted to show you that. And you see here what Pygame gives to us. So the whole thing related to loading assets, to converting them to particular resolution, to managing the game window, to deal with the physics, all this is already in. So after the few lines of initialization, we have the core of a game, so the main loop. And as you see, this is not a very complicated code. We can easily plug in here our own things. So what do you see here? We are running an infinite loop, which runs as long as the ship is not hit by asteroid. We are updating the whole graph. We are listening for the user's action for the keyboard events. We are updating the whole thing, detecting collisions, rendering the view, and displaying the whole thing on the game window. Simple as that. So let's go. with the actual artificial intelligence. Let's go with machine learning. And since machine learning is all about data, what kind of data do we need to do that, to play this game? Let's see what we have on our hands, what is available. So this is the game screen. You see the coordinates, nothing complicated. Also in here, we have the position of a ship. We have a fixed size window. We have 8 asteroids. This is also fixed value. And our spaceships can move left, right. So the game is quite simple, good to start with. We can also calculate the distance from the asteroids. We have its position. We have its speed. It also sounds like a relevant data. And we have a position and a speed of our laser beams. This all might be relevant, but let's start with something which is intuitive and simple. Let's take as our game state representation, let's take the position of the player, of the spaceship and its speed. And also let's put the information related to position of the asteroids. So all this, I think, is a good representation to start with. And this should give us, as an output, a vector of numbers for every frame of a game. So, and what do we want? What do we want on the output? We want to decide which action to do, whether we should move left or right, whether we should shoot or do nothing. So there are 6 possible values here, and we want to predict which one is the best on top of the information which are in the game state. So vector of numbers and the label, the class which we should assign to this vector in the end. So this sounds like a classical supervised learning problem classification. Those of you who had some kind of machine learning activities at the university will know that as a classic problem. It also has classic solutions. So let's start to model a bit. And in order to do that, we need to get training data. So we need to get data which would show the algorithm how it should play. In order to do that, we will simply play that game. And during our gameplay, we will save the information about the state and the action which was done by the player, by the person who is playing that game. So it is also not a very complicated code. You see here 2 other objects which are in the source code of a game. So we have our spaceship, which is player, we have our asteroid, and we are I've added methods which allows us to track information relevant for the game state. So you can hook that in the main game loop. So dump as vector is the actual thing, and it also prints thing on the standard output. I also started to count asteroids which was hit to get the score from the particular gameplay. So also nothing very sophisticated here. So we can save those data into some kind of database, but standard output sounds like a decent database for me in this particular problem. So I was just saving this to the log file while playing. All those data were printed out and saved to the log files. You see here the vector of numbers. So the game states are the first numbers. The last number is the actual action which was performed. And we have data, so everything should be fine. In terms of machine learning is about data. So we have a game state, we have a representation of our problem, we have training data. Let's create a model. I've done this in the Jupyter notebook. It's a pretty neat tool. And I was prototyping with scikit-learn, which is also a quite well-known, well-documented library in Python, which allows you to create and play with most of the machine learning algorithms. So here we're loading the data from CSV file. As you see here at the bottom, we have 760 observations. So it's not I wouldn't call that big data. Nevertheless, it's good to start with. and let's go and create a model. So in first line here, you see how we are splitting our data into the training and test set. We need the training and the test set to validate how our model performs on the observation, which was not seen during the training. And I will use in this first approach, I use the logistic regression, which is simplest possible classifier. And the whole training is the classifier.fit, so it's not a very sophisticated thing also. Then we are evaluating the model, and the classical measure used to evaluate the how good classification is the accuracy. So on the training set we have 78%, and on the test set we have 71%. Is that good or is that bad? To be honest, I don't know. And I will show you in a minute why. Then we are saving the whole model to the file to use it afterwards in our game. So we have a model, we have our baseline, the simplest model which we could have with our representation. So the only thing which left to do is to plug that model into the game. So this is also not a very sophisticated code. I've copied the source code of a game, so I have another version of a game which was played by the artificial intelligence agent. So I'm getting up the serialized model from file, and I have a method which predicts the action on top of the game state. And this also is plugged into the main game loop instead of listening for the events from the keyboard. So it's simple as that. Look at that. Hostile artificial intelligence, or a nightmare came true. It shoots as hell, but not so fast. This hostile, aggressive artificial intelligence is a random agent, so it just takes one random number from this possible range of 1 to 5, and it scores 27 in 10 games. So it's a pretty good strategy to move a bit and shoot a lot. And if this game can be played poorly, logistic regression plays it poorly. As you see, this is our artificial intelligence. So what happened here, we will investigate that in a minute in more details. Nevertheless, it seems that the logistic regression is not has an insufficient information capacity to get the patterns from our data. Or maybe we had too few data. We know that 760 observation is not a lot. So let's investigate this far. The whole pipeline is ready for experiments. We have the whole thing up and going, so we can test different things. So let's use a more sophisticated model. Decision trees are also a classic tool in machine learning toolbox, and random forest classifier is based on the concept of ensemble. So we are taking several decision trees and using them to predict the final value. Just to tell a bit more about how decision trees might be ensembled. Decision tree has its own flows, and they are quite good at, they are quite explainable. You can tell why this decision tree made this kind of decision, not the other. Nevertheless, it also has a tendency to overfit. So if we build a sufficiently deep tree, our training accuracy will be great. Nevertheless, it will not be able to predict on the not seen data. And in order to deal with that flow of decision tree, wise people started to create groups of decision trees with two strategies. One of them is bugging, and the random forest is an example of such a strategy. So we create several decision trees which are relatively small, so 3-4 levels only, and we are feeding them with subset of features and subset of data. So we have a series of predictors, and the final prediction is a result of voting from all of the trees. And this is one strategy. So all the trees are queried, I would say, in parallel. But there is a second approach, which is called boosting, in which we are creating several trees, but the whole idea is a bit different. So we are creating one tree. It has some predictions which are good and some errors. So we take those errors and we train another tree. This also has a portion of good predictions and bad predictions. So we take those bad predictions and create another tree. And each of those trees has its weights because of the number of handled observations. And on top of that, we are getting the final outcome, final prediction. XGBoost is an example of implementation of boosting strategy. I will use it also in the following slides. So this random forest is awesome because it's, as you see, 100% accurate classifications. So let's see how this one performs. It starts much better. It's our ideal aggressive artificial intelligence. But in the end, it also ends in the corner waiting for death. So we can sleep without our nightmares about artificial intelligence ruling the world. Random forest is also not the future Skynet, at least in this case. So let's try something different. And before we go further, I wanted to tell you a bit about things which we observed here. So in machine learning, there are two terms, underfitting and overfitting. And good model is something between those two. So we want, when we are dealing with underfitting, we are having a very poor predictions or classifications on the test set, which is a clue that this model is too simple to handle a particular problem. And on the other side of it, we have overfitting, which can be compared to the student who knows the answers for the questions from the previous edition of exam, and if the lecturer decides to use the same question, he will perform great. Nevertheless, if the lecturer decides to give different questions, this student does not have general knowledge to solve those puzzles, and most likely he will fail. So on the training set, we have a good accuracy, for example, and on the test set, we have poor scores. And as I said, decision trees tend to overfit a lot. You need to be very careful when dealing with them to not overfit, and there are solutions for that. And we will come to that in a minute. So just to conclude this first portions of problems. So in case of this particular representation, simple models are not enough. Most likely, simple models are also not enough for these problems. Nevertheless, they are quite good baseline to compare with. And 760 is too few, so we need to play more. We need to generate more training data to perform better. And the last one, model accuracy, or the, as we call them, offline metrics, are good to assess the potential of particular solution. Nevertheless, we, as with the software also, need to test this and deploy this into production and see how it performs. So let's get more data. Since machine learning is about data, as I said, we might have too few data, and let's extend our representation of a problem. So when we are playing in the game, we are taking an action on top of that, what we see and what we have done in the past. So adding a memory to store information about previous game state might be a good experiment to bet on. And here, how this representation performed. XGB classifier is the boosting strategy implementation. MLP classifier is a neural network, deep neural networks of several layers, and logistic regression is logistic regression. So you will say that logistic regression shines here, so given more data helped. No, in fact, it didn't. So the spaceship stands on the center of the screen and shoots all the time. And so this might be our second baseline. So we want to compare, we want to perform better than random and better than this kind of simple strategy. So dog barks in the space, and we are going further. So increasing the complexity of state representation, which we have in fact done, is not the best idea when we don't have any working solution. So if you think about this, we have 40, 50 long values in this vector. So this gives quite a significant problem space to reason about. And to handle such a huge space, we need a lot of observations. And this might not be the good idea when we don't have when we are not sure if this representation gives all the information. So exactly the same as with everything in life, premature optimization is the root of a lot of evil. So be aware of that. And at some point, this whole project, I could say, became some kind of family activity. My children were coming to me and asking what the spaceship have learned yesterday. Is he playing smarter than you, Dad, or not? Thankfully not. And I will spare you all the other experiments which I have done. All of them are documented in the repository with the examples for this presentation, so you may go there and laugh at me in your free time. And I will go to the representation which gave a bit better results which I decided to share with you. So let's split our game board with this kind of grid. Let's create a matrix 6 to 10, which represents the board. And each cell in this matrix contains information about number of asteroids in that particular cell. So here we have a bit of a Python code, and then we are also doing a translation of a position of a ship to the same coordinate system. As you will see in a minute, the resolution of that grid can be adjusted because it might overlap with the ship. We want to ensure that the ship is in the one row only. And this was one of the lessons I've learned also. So the resolution of a grid is, as it is called in machine learning, a hyperparameter, so something which we can tune afterwards. I've also added them, so initial experiments were quite okay, and I also added information about the previous state, and it gave me the following results. As you see here on the GIF, it plays a bit better. It even, I was surprised that he was even capable to escape from the rock. So it was also done on the relatively small amount of data, of training data, so 5,000 of observations, so also not a huge amount of data. And the whole architecture can be tuned. Nevertheless, it looks much, much better. Let's go. So we have a working solution. We can tune this afterwards. We can add, as I said, tune the hyperparameters, change how the networks, how the neural network learns. We can also change the number of training data. Nevertheless, it works quite okay. So good representation and good model might work even on a small amount of training data. And as you see with this grid, in fact, we have limited the number of possible game states. So this helped to understand this problem, to the agent to understand this problem. And okay, what's now? We have something which plays quite okay. But let's think a bit about the optimal strategy for this particular game. It's a simple game, in fact. And if you think about this for a second, the optimal strategy is, in fact, going from the left to right, shooting all the time. This gives us the maximum score and also keeps the asteroids far from the ship, so we won't get hit. And what can we do to implement such a strategy with the machine learning? So here, in fact, the simplest possible set of data which are required to do that. The first row in each column is an action, and the second column is this is a frame count. So we are just I was just trying to teach the neural network to mimic, to do exactly the same as I did by teaching it a sequence of moves. And here is how it works and how it performs. So it is, in fact, the optimal strategy. So the score is very high. It's much higher than the score obtained from the machine learning, from the previous machine learning algorithms. What does this say to us? So this optimal strategy is a thing which we are sneaking into this problem. We are sneaking this by playing ourselves. So this is all by doing such a trick like that. And so this is in fact not an artificial intelligence, but it may be intelligent behavior, mimicking of the intelligent behavior from a human tutor. So, but to conclude this particular experiment, if there is only one known solution as this optimal strategy, you most likely don't need machine learning to solve that problem. And this is evident because this kind of, sequence in time can be easily implemented in few lines of code. And if you want to introduce machine learning to your particular project, think twice, then think one more time, because it increases the complexity of whole thing a lot. So if you can leverage increments which you get from machine learning by the scale of the whole thing, like in Allegro we are doing this for the search results ranking, a lot of people are using this, and even a small increment gives us a lot, then go on. But nevertheless, if you have a simpler solution at your hands, go for it, even if this not solve all the problems. So, okay. So this is one particular game. What about other? What if we would like to have something which can play any game and come up with the optimal strategy for any game? So this sounds like a GAI, General Artificial Intelligence. So what about that? So there are different approaches, but I remember from the university times that there is something like evolutionary algorithms. Maybe we will try this one. Maybe this will help to bring the algorithm which would come up with this optimal strategy, which I gave to the algorithm from my own knowledge. And this would be something. But the question is for you, are you really into gaming? I am not, as you know. I am lazy, I don't want to play games, but it is something hypnotizing in looking at how computer plays the game. So this is really nice, to sit there and look how computer plays game, yeah? So if you can open several windows, and it's also even better to look at this. So what can be better than that? I'm sure that you would agree that two computers playing the games for us might be better. So what can be better than that? Cluster of computers playing the games for us. And so we don't have to look at this. We just have a Grafana or Kibana. So work habits die hard. So we are looking at those different charts every day in our daily in our work. So I also wanted to have this kind of thing because the evolutionary genetic algorithms are pretty neat to parallelize. So we can run several hypotheses in parallel, and this speeds up the whole thing. And piping gives us a handy tool for that, so we can change the video driver to a dummy one, and this allows us to run those games headless, so we don't have to look at them anymore. So this is the one for really hardcore players only. So let's get into the genetic algorithms here. So how to model this particular game. I will also refer to the Shmoop because you already know that game. how to model evolutionary algorithm for this particular game. So in genetic algorithms, we are working with populations which consists of individuals. And the individual in our case is a sequence of moves. Those particular moves in the sequence, we can call them chromosomes, you can call them genes. And so we have our initial, I was working with 6 individuals in the population. You can change that number. And what we have done what I have done in the second step, so all those sequences were fed to the game, and I was evaluating them by playing games several times to get the average score. There is a sort of a randomness in the game, so those asteroids are lying at different angles and different speeds. So in order to have a good evaluation of given sequence, I was running it 4 times. So let's on top of that, we can take the best sequences and then do the selection of the best individuals in the population. Those individuals are allowed to cross over. They can have kids, and we are creating the second generation using that. You most likely see that I am leaving the sequence number 4 is the best one. I am leaving it in the population for the second generation. Crossover is in fact an exchange of the half of the genotype. So there is a chance that those genes which were the source of the success of the given individual will be lost, or the sequence of genes. So I decided to leave it here. And the second step is the mutations. So we are changing randomly some part of the genotype. In order, this should help us to leave the local optimus during the whole optimization. So this is the idea, and then the whole thing repeats many times. So the idea is quite simple, and here is how one of the sequences which performed best look like. It came to this point that it moves from the left to right. So there is a chance that after continuing this evolution for some more time, it will get with the optimal strategy. Nevertheless, it lasts quite long to get to that point. And that's why I wanted to show you the carpet from the bedroom of my grandmother. That, in fact, is an experiment conducted by the people from Berkeley, and it was intended to show you how hard it is to understand the environment which we have no clues about. So this bluish square is our agent who plays the game, and it goes through the game board. It doesn't know if he can move left, right, if he can jump, what will happen if he touches this particular square, will he die or not. He needs to play the game and learn that by heart. And since you don't have any clues, and this looks like a carpet, not like a game, it's really easy to understand how difficult the problem is. And in order to explore the whole space of possible solutions here, the very bright people came up with reinforcement learning. And I'm sure that some of you have heard about DeepMind and the development in the area of deep reinforcement learning. These are the 3 papers which were published, and a few months after the DeepMind was acquired by Google. And what they have done is they created an agent, the deep reinforcement learning approach with the neural network, which allowed them to play better than humans in most of the classical Atari games. So how this one works. Reinforcement learning is based around the idea how we people learn things. So in order to learn things, we interact with the environment, and we get the feedback from the environment or from the authority, like a tutor, which tells us whether we have done something in a good way or a bad way. And as a result of that, we are receiving reward or a penalty. So we can easily interact with the environment, we are getting the rewards, and on top of the subsequent state, we are also making a decision which action to take. Sounds simple as I don't want to say what. Nevertheless, it brings a lot of challenges, both on the theoretical side of this and also on the computational and algorithmic side of this. And the approach described by DeepMind, before we jump into that particular solution, I want to bring some more definitions here. So the state is a thing which we already know. So we have a state of a game, and we will also need rewards. We need to define which things are good for the agent and which are not good. So in case of Shmoop, we don't want to be hit by an asteroid. So this kind of situation may be related to the reward of 0, or the reward might be negative. And we want to hit the asteroid, in fact, many asteroids, so the score might be different for hitting 1, 2, 3, or 4, and we want to stay alive. And in this in reinforcement learning, we are not dealing with the classifier, which on top of the game state are given the particular action. We have a thing called Q function, and this is a subtle difference here, because it tries to estimate reward for a given state in a given action. So you can imagine that as a lookup table, as you see here. So for a given state and a given action, we are estimating that it will give us the reward as is written here. It also can be probability of getting the positive reward, and the whole algorithm can be summarized using this quite simple pseudocode. So we are initializing our Q table or Q function. In the beginning, it will return as default numbers or random numbers, and we apply game a lot. So it's similar to evolutionary algorithms in that manner. But in evolutionary algorithm, this selection function is very simplistic. And here we are based on the estimate of the best reward, and this reward may be related to different things. So Qtable, we are asking Qtable to get the best action for the given state, the action which maximize the possible reward. We are playing the game with this action. We are getting the feedback from the environment, so we are memorizing the reward which we received and updating the Qtable. And we are doing this as long as the agent is alive, and then we repeat. Whenever we repeat, the Qtable, Q function estimator, becomes more accurate, and it allows us to effectively explore the solution space. So what the DeepMind guys did is also a different representation of the game. So they took just the same thing as we have while we are playing the game. So they took the pixels from the actual frame of the game. It brings a lot of different possibilities, because you don't need to plug into every game which you want to train an agent for. You can just learn to play game by watching YouTube, yeah, which was the title of one of their papers. So they are taking the pixel as state representation. They are taking 4 frames of it. So we are operating on 4 images. So this opens also some interesting possibilities in terms of machine learning. They were able to use convolutional neural networks. And what is a convolutional neural networks? This is a concept based from the computer vision. So all those artificial intelligence tools which allows you to distinguish cats and dogs on the YouTube videos are using that. And convolutional neural networks are based around the idea of convolutions. You can think about convolution as a sort of a filter, which extracts the particular feature from the image. And those networks are usually pre-trained on the huge data set of images for a different problem. For example, there are data sets like ImageNet, which contains several millions of images annotated manually, and all the elements on those images are described and labeled. And the convolutional neural network can be trained on this data set, and it learns which features of the image are relevant. And this kind of network can be taken, this is called transfer learning, and used to solve different problems. We are just splitting the final layers of the network and using those convolutions trained on the general problem to solve our specific problem. And this is what they've done here. So they took the convolutions, 3 layers of that, and they then afterwards built a quite classic neural network architecture. I will not go into details here. Nevertheless, this is in fact quite simple neural network, comparing to some used in nowadays. So they took 4 frames and they've trained the agent, and here is how the agent plays in a well-known game after 240 minutes of training. You would agree, I guess, that it plays quite okay. After the more training, it will play better. And if you are interested in playing with this kind of old games, also OpenAI is into that. So OpenAI is a company which also tries to push the boundaries of artificial intelligence further. And reinforcement learning and deep reinforcement learning is very heavily investigated. Very heavy investigated direction here. So if you want to play with those games, they give you an environment called Gym, which you can easily play with some games from emulators. There are your task is to build the architecture, build the agent, and they will allow you to evaluate and benchmark with the other people who have tried to solve those games. So to summarize, machine learning consists of many tools, many stages, and on each stage you can do a harm to yourself. So problem representation, how we phrase the problem which we want to solve is important. And then the data which we are taken to solve this problem is also important. Then we need to get training data, decent amount of this training data, and this depends from the model which we are using. Most, or maybe not most, I'm not able to say that, but there are a lot well-performing linear simple models. For example, in AdTech, the linear regression, which is the simplest tool to predict the value, are used heavily. They are fast, they are easy to train, and they solve this particular problem which they have. So they are able to deal with a lot of data, and they are able to predict very quickly. So choosing the model is the second thing. And the whole thing is rather a set of experiments to do, there are usually not only one possible best universal solution. You need to experiment quite a bit. And if you have a working solution, you can tune hyperparameters, because all those models have a lot of different knobs which you can play with and change, for example, the learning rate, change the number of features, change the number of layers, and so on and so forth. And finally, the whole thing does not requires to be tested in production. So as you saw the spaceship, on the paper the result looks good, and when we are putting this into production, the spaceship is doing weird things, like with this logistic regression staying in the center of the screen and shooting all the time. So the whole thing was quite funny, quite interesting, and I will continue that. Nevertheless, the whole machine learning thing requires a lot of patience because models which we are, for example, using in production trains for quite a while, and working with such a long feedback loop is far from being comfortable. So all the examples, all the source code, how I hacked the shroop is available here on my GitHub. Go and take a look if you are interested in this kind of experiments. And there are multiple games with open source code available in the internet. And if you are looking for the problem to solve to train your machine learning skills, I think that this is a really neat case to solve. I was brought into the coding because I wanted to create games. And this is, I guess, also a case in here. So I think that it is worth to explore if you are interested in AI-related topics. So if you have any questions, we have time for them. Let's take a look. No, I didn't try to limit the number of lasers shots which the ship can take. It would be also a very nice constraint to introduce here. Maybe I will do it in the future. And that's why I cannot compare this to the human solution. The closest comparison is this optimal strategy which I show you in the middle. So going from left to right, it's scored around 300 points. And this is very close to the score which you would have in that game. So if no other questions, thank you very much. I am here available to talk. And once again, thank you for coming to this session.